Hello, everyone. This week, we will talk about energy and climate change. This is a very big topic, and we will try to focus on the integrated assessment model that link emissions from fossil fuel consumption to the impacts of climate change through the change of concentration and the socioeconomic impact of the warming, and that link to the implications, policy implications of different mitigation strategies. So as you can see, the emissions come from our fossil fuel-based energy system to the climate impacts and the policies that can address those impacts. It's a long chain, but hope this lecture will give you some sense of what's integrated assessment model and how we use it to do some of the analysis. Also, we will discuss the evolution of the policy source to address climate change, such as the wages idea, the cost curve idea, the best practices idea, the social cost of carbon idea. Those are, you can see the evolution of those ideas, and each has its pros and cons and the limitations. So we will discuss those too. And lastly, we will discuss the climate change impact to our energy systems, both from supply and demand. Those will help us understand the interactions between climate change and energy systems. So energy systems impact climate, that's through what I just mentioned, but at the same time, climate change will impact the energy systems. So this is a big topic, but at the same time, we will try to focus some of the key messages that we hope you will understand. Sample analytic questions. Each lecture, we will try to give you some inspiration of those questions, real world questions. For example, if all fossil plants stop generating from 2023, how that will contribute to the climate mitigation. There are a bunch of research on that. Say abruptly stop generating from a certain point, or all fossil plants, no new fossil plants were built, and all fossil plants continue running towards their lifetime. What's the implications? Those are very good questions, and it's helpful for us to understand those questions. What needs to be included in the New York State scoping plan to achieve goals in the Climate Leadership and the Community Protection Act? I'm serving as in the advisory group for the scoping plan. And if you were asked the question to provide comments on the scoping plan, for example, to achieve the Climate Leadership and the Community Protection Act in New York State, what's your recommendations? Those are real questions. What level of a social cost of carbon should New York State use? We will introduce the idea of a social cost of carbon, but what New York State should use? What factors should we consider, and how to come up with reasonable number that not too high, which sounds unrealistic, and same not too low, that makes little differences. how climate change would affect energy supply and demand. We will talk about this. Different technologies, different systems have different response to the climate change. So those are some questions that this lecture will help to address. First, the integrated assessment model, or IAM. You might hear this term in some occasions. It represents a series of models that started from the basic assumptions such as GDP, population, policies, and other assumptions that link our economy, energy systems, and impacts to land use systems and climate. So it produces the impacts, climate impacts, such as impacts to economic outcome, impact to emission changes, impact to our energy pathways, how today's investment towards middle century or to end of the century will have a different outcome, and impact to the land use, for example. So it's a series of impact or response functions that link our energy consumption, which emit greenhouse gas emissions, which cause the warming climate, which has impact on our economic, socio-economic, impact on how we choose our energy system, have an impact on the land use, or water and air pollution, even human health impact, as we discussed in last lecture. And integrated assessment describe the macro level of modeling practice that try to link all those elements together as integrated system. Very often, those models produce the results that can help us to understand the impacts, or help us to diagnose, or at least visualize how certain policies, for example, specific in technology policies or specific mitigation policies or specific technology can contribute the mitigation, and IAM can help us to understand those relations. Typical examples is the IPCC reports or assessment reports. And now it's the 6 rounds of reports released, starting release last year and this year, and there are more coming. There are a series of reports. Some focus on impact, some focus on adaptation, some focus on mitigation, and so it has different focus, but it's all try to assess the impacts and our pathways, or how we address those questions, or the climate changes. Some may say, oh, the impact report is showing climate change really have dramatic impacts, and the mitigation report just still we can do something about it, right? So those are, and the synthetic report has not released yet, and it's still in process. And this is example of the risks or impacts of different scenarios. And those scenarios, as you can see here, SSP It's shared socioeconomic pathway with the different assumption of GDP, population policies, and other assumptions. Each represent one type of a shared socioeconomic pathway, and their impact to the risks of terrestrial and freshwater ecosystem, for example, impact of risk of smell, and impact and risk to ocean ecosystems and climate sensitive health outcomes. And you can see those models generate the results that help us to understand the risk level. It might not sound intuitive, but it offers the high-level results that can help us to understand the impacts. And as you can see here, SSP 1 to 1.9 represent a level of less warming climate within 1.5 degrees C of warming. That's what the desired outcome. But that involves quite efforts to achieve that. And that's what this chart shows, the mitigation gap. And here are the projected global greenhouse gas emissions from national determined contributions that each country announced their national determined mitigation policies or regulations before UN Climate Conference COP26, and compared to the desired outcome. One is because the goal is to at least control to 2 degrees C, right, by mid-century, under 2 degrees C, and try all efforts to achieve as much as no more than 1.5 degrees C, right? So that's the blue range, and this is a 2 degrees C in the green, light green range. And the trend from implemented policies here, and even include the announced national determined contribution, NDC, and it's following this path. And some are conditional, some are unconditional, include all unconditional elements. It's possible we can achieve the 2 degrees C element, but still fall short to achieve 1.5 degrees C goal. And the policy assessment for 2030, as you can see here, we still have quite the emission gap that we need to achieve compared to the desired pathways or carbon emission pathways. No need to say those in 2050 and 2100. And by then, we basically need to completely decarbonize our energy systems, our human activities in order to achieve those goals. So the differences between the implemented policies and those desired outcomes is what we call the mitigation gap. And from here, the mitigation gap is ranging from if we minus 60 to 10 is about 50 gigatons of CO2 emissions each year. If we use 2050, that's the gap we are describing. And there are a lot of work to do, and each country needs to contribute its portion. And that's exactly what makes the mitigation strategies difficult. And there are quite a lot of political, economic, technological, and other or international collaboration considerations in when discussed the mitigation strategies. Mitigation pathway. So think about, we know our goal, and that's no more than 2 degrees C, and as much if we can do 1.5 degrees C. That involve deep, rapid, and sustained emissions reductions. And that also require to deploy renewable energy, low cost, lower carbon technologies, clean energy, at the speed and the scale that needed to achieve those goals. And as you can see here, basically need to achieve to reduce and achieve net zero carbon emission by mid-century, and negative emission if we think about to carbon neutral and to first stabilize the carbon concentration and then reduce the carbon concentration. How the energy system should respond to here, also from the IPCC report, and from different models, as you can see here, message, remind, GCAM, each represent an IAM model by a different research group. By the way, those are very famous models that if you're interested, definitely I encourage you to search those names and know more about how the model work. But those models generate results. On the left side are the baseline for 2000 or by end of the century, basically continue the business at zero. And the right-hand side are the mitigation or the energy system that can help us to achieve the temperature control goals compared to the baseline. As we can see here, we need a lot more on the efficient energy efficiency to reduce the demand. Each model produce slightly different results, but as you can see, the elements are quite similar, and increase the scale of solar CCS and reduce the need for coal, biomass, oil, gas. So that's this scale and the trajectory that all the models deliver. And the scale might be different of each technology, might be slightly different, but the message here is really make use of the role of energy efficiency and double down the efforts to expand renewable energy and other lower carbon technologies. At the same time, phasing out fossil fuel energies. Those are the models that based on its different assumptions. Some are common assumptions, and its projections of the future energy systems. Those will help us to understand what are the pathways to achieve the desired outcome. And that's the role for what the integrated assessment models can contribute. Technology-wise, some you can say the technology are commercially available, except some technologies such as CCS. Even for CCS, it's about costs. So as you can see here, this chart is a little bit hard to digest, but on the left side, it shows the emission intensity of electricity. That shows fossil technologies has higher emission intensity, so the lower the better. And some technology are pre-commercial technology, mostly CCS and ocean wave and tide technologies. On the rest side are the levelized cost of electricity, as we discussed again and again. It's an indicator to show how competitive the technology compared to other technologies. And as you can see here, the lower cost, the lower carbon technologies, renewables, are achieving grid parity. They are competitive with the conventional technologies or fossil-based technologies. And that's good news. And IPCC reports also incorporate those recent developments and really show it's possible and technically possible and also economic viable to really achieve energy transitions. So those are the key messages or fundamentals, and the IAM really help us to understand the logic. And so what are the key ideas behind those to address climate change? What to the policy? I need to, so we know the impacts, right? So what are we going to do? Going to deal with it? There are evolution of the policy community and research community, and how we really think about those challenges. One of the famous paper is Pakala and Sokolow. Both are professors at Princeton University. They published this highly cited paper, the mitigation wedges. The idea is, so if we compare the business as usual, which we do not, or doing just what we have been doing, then we are in a trajectory to reach high emission. And in order to achieve our goal, we have a pathway, right? So that the difference between these two pathways is the emission gap, as we just discussed. That emission gap is very big. And here it shows to stabilize. I mean, those numbers might seem out of date, but the idea is there. Between the gap is about 10 gigatons of carbon in this chart. And it's big, right? So we don't know how can we going to achieve it. And one main contribution from this paper is, if we slice it to different slices, if we cut it to different sizes, and each slice represents one type of a technology. It can be renewable, it can be CCS, it can be industry transport technologies, EV, for example, or hydrogen. And we know how big scale of those energy use and the carbon emissions, and we know what technology is available, and we know exactly how to achieve it. So the wages idea is really divide the emission gap into tangible technology pathways that we can deliver. So the message is very simple and strong, that we have the technology, and with the technology we can achieve it, and we just need to make clear of the technologies and how we can deploy the technology at the scale needed. It's very powerful, right? So, and the message is very clear. That's the why this paper is very influential. But it has its problem, right? We know the technology is ready, and we know we have the tech, but how about the costs? That's something the wedges idea doesn't discuss much. Yes, it discusses costs. That's why it shows its technology are technical available. So that's evolved to the next kind of a mitigation idea, which is the Mckinsey cost curve, or Mckinsey curve for short. This is a typical type of chart, as you can see here. It has two dimensions. One is the cost, which improve the wedges idea, right? And what's more, the vertical axis shows the cost. That's the cost, abatement cost is the cost to reduce 1 ton of carbon dioxide from the atmosphere. And the horizontal scale shows the cumulative mitigation potential of all the technologies. So for each technology, it has a cost. Some are elective. That's very important to interpret this chart. For example, energy efficiency, to change light bulb to LEDs, for example, to combined heat and power with some minimum upgrade. Those you can immediately get benefits without too much investment. And elective abatement cost means that you can actually make money through its lifetime. So with this, each plane, or you can see here, it has a cost and it has how much it can reduce it, and you rank the technologies from the lowest cost to the highest cost, abatement cost, and that adds the accumulative mitigation potential. So basically it ranks the different measures which we should take priority, those measures that can reduce carbon emission with selective mitigation, which we make money from doing it, or save money from doing it. Those are the priorities. So the wages idea doesn't show the costs. It only shows all different technologies can do it. And with the Mckinsey curve, it adds an economics component in the discussion and rank different measures or technologies with its cost. So we know what we should do first. What are the priorities? And we know in order to achieve certain carbon mitigation goal, what are the technologies we needed to do? And for those that's not yet technological or economic variable yet, for those with positive, we know in order to achieve what a carbon price we should do. Let's say if we want to achieve 2 billion tons, for example, right? So we know roughly here, and the cost is about $30 per ton. That's a lower cost, right? Compared to other studies, but this is it's an out-of-date number. If they are doing the same study today, they would have different number, but the idea is there. So it shows what costs can deliver what level of ambition and how to prioritize those different technologies. So that's the new developments of how we really see the evolution of our policy developments or ideas, right? So think about the question: what's the problem of a Mckinsey curve? Yes, we know the cost, but can we really do it? And sometimes cost is not just the only consideration, right? And for developing countries, they don't have the technology. Even the cost is cheap. So that brings another level of ideas. I'll come back to the social cost of carbon. Let's see. Do I have the oh, sorry. Yeah, here. This is the best practices idea. So we know energy efficiency good, and we know we need to do low carbon eco-city renewables. Some sectors are more difficult than other sectors, and different policy and technology instruments have its own limitations and strengths. So the best practices idea is, yes, we don't know how to do it, but let's explore some ideas that are already doing very well. Best practices. Some countries are good at some technology, some countries are good at some policies. And let's do assessment of why this country has been successful in certain technologies. For example, Denmark on the renewable integration using offshore wind and using the combined heat and power to store those excessive wind generation and produce when it is needed extra generation. So those are examples of best practices and how those best practices are fitted in its own local condition, and which offer some inspiration at the same time implementation details. If this country can do it with this very similar resource-based context, technology, maybe you can do it too. So that's the idea of best practices. So let's find what's work, what's not, and we create best practices and what makes those best practices successful. So we can translate those best practices to widely more successful implementation. As you can see, many international organizations are trying to push in that direction. So to create case studies and best practices and the toolboxes, technology database. to help policymakers to implement. So those are the involvement. Now I'll back to the cost, right? Cost is very important, and so how we can improve the assessment of a cost. What's the real cost? That's the introduction of the idea of social cost of a carbon. So the cost of a carbon is not just it's complicated, right? So depends what costs you include, what's not. And climate change has impacts. Here is a chart from the paper, the review paper, to significant systematic assess the socioeconomic impacts of climate change. As you can see here, climate change might cause mortality, damage to building, to infrastructure, to all different to agriculture, for example, grain harvest, labor supply, because human productivity also relate to the temperature. So those charts has very similar design, right? And the horizontal, it's usually the temperature, and the vertical axis are the impacts, and you would observe a tipping point, which is very often human most comfortable, most productive temperature, for example. And here is an example of socioeconomic impacts. Many economists spent quite a lot of efforts to try to get a quantitative analysis out of the data and literature to show the damage functions, as you can see here. So with damage, you would know the costs, right? So social cost of carbon is the marginal cost of a carbon, which means if you emit 1 extra ton of carbon dioxide to the atmosphere, what the damage it create. So that's the cost of social cost of carbon. So basic economics is, if we introduce a carbon tax or carbon price that equals the social cost of a carbon, then we would reduce the impact. That's the optimal price for how we regulate carbon emission, which means the impact is compensated by the cost or the carbon price. Very often the costs included in social cost of carbon are elective agriculture productivity, human health impacts, property damage, energy system costs. But costs not included some unknown impacts. This can be physical, ecological, economic, or even psychological. And there are also some unknown costs, for example, information with climate change we need more efforts, and those costs are a lot included in the costs. And psychological cost with the catastrophic impacts really impact our psychological, right? So very often costs include financial and economic damages, but less on the physical, ecological, and psychological, and some the unknown costs or unknown impacts. If we need calculate, we have to know the impact, but they are unknown impacts, right? So the idea of a social cost of carbon is based on the economics of regulation. And EPA, for example, really tried to push towards that, and is to introduce they incorporate the social cost of carbon in its policy or regulation. And it has 2 rounds of study. One is the or guidance. One is the 2010 assessment. As you can see here, if we describe using 3% of average discount rate by 2030, it's roughly at $30 per ton of carbon dioxide. And the 2050 number raised that to about 50 using the 3% average. For sure, as we discussed, the discount rate will impact the results. And the higher the discount rate, the higher the social cost of carbon would be. But 30 and 50 is roughly the scale of 2030 number. 2050 is much higher. And we can compare that to the New York Department of Environment and Conservation. Also want to introduce the value of carbon, and which has much higher number, about $125 per ton. And you may ask why. You may say New York State has comparatively higher level of socio-economic development. Those therefore the cost would be higher. At the same time, many aspects would impact the social cost of carbon. I mentioned the development level, the value of a statistical life, and how you count those damages will all impact the cost of this social cost of carbon. And more recently, a paper published by a group of scientists who study IAM models and social cost of carbon for long, and it's well established some models in the studies, and publishing results to update social cost of carbon, because there are new evidence, there are new impacts incorporated, and try to introduce the distribution of impacts, which gives more reasonable results. And the updated results is run at about $185 per ton, which is comparatively higher number, which shows we really need to incorporate the cost of carbon in order to achieve the mitigations or desired mitigation goals, which a cost of carbon will for sure help. But as we will discuss more in here is, if carbon price is the ultimate optimized instrument that economics target to introduce, why it's so difficult to implement such a policy, because people doesn't like new tax. A tax is always a very hard sell. Rather, different governments choose to create subsidies for green technology, for clean energy. So it didn't have new tax, but it created incentives that will attract the deployment of renewables or manufacture of those technologies. That doesn't mean there's no space for tax, but um, it has societal political acceptance issue. Also, regulation was market. The social cost of carbon is based on assumption of a workable market that would have a value for those impacts, and also would have response to introduction of a cost. But in certain contexts, regulation, such as energy efficiency standards, could be more effective because you need any of this, you need information, and the information is not free. And there are also behavior barriers that you simply do not have the time and efforts to know how the market works. But if you just buy the most efficient products and use it, then that's simple, right? For example, if you buy a new washer or new heat pump, you may not have the full information to figure out which one is better, which one is more energy efficient. But if there are only high efficient products available, then you just buy it. So that's one example for what works, what not, and there are quite a lot of research out there, and I just summarize what's the debate there. So for in the real policy, really need to consider social acceptance and political feasibility, and new discussions, new ideas that is trying to incorporate those limitations and considerations in the integrated assessment model, so the models can have better outcome, better projections of what works, what not. Mentioned the best practice idea, which try to address, even it's cheap, why people is not doing it. So we need to make some inspiration that it's doable, and some other countries really doing it well, and maybe you can do it. So best practices. Yes and no. So the problem for the best practices idea is maybe Denmark can do it, you can do it. That might not true, because it has very different context, very different technology endowment, very different resource conditions. So each best practice has its own foundation or supporting technical, political, and socioeconomic context. And those are very important for this technology success. So in addition to best practices, maybe those contexts also important to think about, to incorporate. So that's the next level of thinking, how we can introduce toolboxes, database, so policymakers can choose from those instruments, database, and based on their own conditions. From wedges to the cost curve, to the social cost of carbon, to the best practices, to a more comprehensive way of thinking about the policy tools, policy instruments, and their supporting conditions reflect the evolution of the policy discussion or debate in in the research and the policy community. I hope it captures some of the main ideas and why it evolves, because those ideas has its own merit and has its own limitations. Lastly, I want to spend a few minutes on it's not just energy creating emission add the concentration, and concentration has an impact to the climate. That's the logic from energy to climate, and the climate also impact our energy system. This review paper, which I also outlined in the reading list, really look into how climate impact different energy technologies and systems, some at a global, some at a regional scale. Some impact might be good, some impact negative to the production and the costs of our energy systems. So here it shows different scenario and a different timeline. So in general, climate change would add the cost of the energy systems. That's for different reasons. First, it adds risks, more frequent disasters or more severe events can create uncertainties, and that has a cost. For example, the extreme cold weather during the winter 2020 in Texas, and many people died from it because it has impact on the gas supply, and power plants has to shut down, and there was no electricity in extreme cold weather. Then that's a disaster. So warming climate also add more costs on cooling, which reduce the efficiency, and it also impacts the availability and the distribution of solar, wind, and other renewable sources. So this chart summarize how the different climate scenario would impact our energy system, and it's not always good news. And overall, it at the cost. So that bring up the idea to link climate models and the energy system models to have interactive modeling practice between these two groups, right? Conventionally, climate modelers focus on how emission will change the climate, and the energy models respond to how the energy systems can achieve the climate or the temperature control mitigation goals. But climate impact energy system, our energy system also respond to climate change, and especially for renewables, which very highly depends on the weather or longer term climate change, and those would especially, and that's also why high resolution of the models will especially demanded for such interactions. And the better the climate models can enrich or help provide the inputs for the energy modelers, and the energy modelers can provide the outcome that the climate models can incorporate. So it will help us to have better modelers, both in the climate model community and in the energy modeling community. So this is another emerging research area that can link climate and energy system models. So to summarize what we have discussed today, so we started by introducing the integrated assessment model, its framework, and how it was used in energy emissions and climate impacts analysis. And we also take the opportunity to introduce the evolution of the climate policy instruments from the wedge idea to the Mckinsey cost curve to the social cost of carbon and to the best practices and to the toolboxes. It shows how the policy community really developed the idea, and it's very important to understand the applications and limitations of different policy instruments and know what's work or what's not, and how we can have better modeling in order to incorporate or improve those limitations. Climate change is the outcome or result of our energy system, but at the same time, climate change also impacts the supply and the demand of our energy systems. So it's very important if we think this as an interaction and try to improve the modeling of both systems. That's all for today. I hope this helped you to summarize our discussions. Thank you.